Hi, so we've got some amount of substance or mole questions coming up. They're taken from OCR past paper questions, year one of the specification. Um, as always, you can pause the video at any stage, have a go, and then the answer will follow. Okay, so here is the memorizable content. Being able to pick out what variables you've got from the question and what you need to work out from the question is going to be linked to a solid knowledge of these equations, and it's particularly useful if you know the units, because it gives away from the units which variables you've got. So as soon as you see mole per decimeter cubed, for example, you know you've got a concentration. It's worthwhile pointing out that I've used G for mass of substance, because that has got to be mass of substance in grams. On the AQA specification, Avogadro's number is given the symbol L, whereas I've used capital N subscript A. So just a couple of things to watch out for there. Okay, so take a look at the question. We've got a balanced equation. We're told that we've got 0.005 moles of calcium nitrate, so that's the amount N of calcium nitrate in moles, and we're going to collect some gas. Look at the state symbols. The NO2, the nitrous oxide, and the O2 are both gases. So for every mole of calcium nitrate solid, we can expect to collect 2.5 moles or 2.5 moles of gas. We've also got this term towards the end of the question, at room temperature and pressure. You have to know that 1 mole of an ideal gas will occupy 24 decimeters cubed at room temperature and pressure. Another important skill is being able to convert between units. Now this is a multiple choice question, and we've got answers in centimeters cubed. So 24 decimeters cubed of a gas is 24,000 centimeters cubed. So 1 mole of an ideal gas will occupy 24,000 centimeters cubed at room temperature and pressure. So the amount of gas produced and the volume of gas produced, there are a couple of little hints as to what you're going to need to work out here. So from the amount of calcium nitrate, because 2.5 moles of gas are made for every 1 mole of calcium nitrate, we can work out the amount of gas that you'd expect to obtain from 0.00500 moles of calcium nitrate. Because it's at room temperature and pressure, we can use the relationship that the volume of gas produced is 24,000 N, 24,000 because we are working in centimeters cubed. Put the numbers in, that gives us that amount of substance in moles. Multiply those two figures together, the 24,000 by 0.0125, and that gives us an answer of 300 centimeters cubed. Okay, so in this question, we're going to have to work out the number of copper atoms in a coin. So the coin weighs 5 grams, and to get the question started, we need to do a percentage calculation. Only 84% of that 5 grams is indeed copper. So first of all, we're going to need to have to work out the mass of copper in 5 grams. Then we can work out the amount of copper in moles. Don't forget, you can always use the datasheet to find out the molar mass, in this case the relative atomic mass of substances. So need to refer to your datasheet to get that relative atomic mass for copper. The number of copper atoms, we're going to have to use Avogadro's number. Now this is an OCR question. Avogadro's number is on the datasheet. Other specifications such as AQA, they will give you the value for Avogadro's number and other constants that they'd like you to use. So in short, just use the data that you're given. If in doubt, 6.02 times 10 to the 23 for Avogadro's number. So the mass of copper as a percentage, so 1% of 5 grams is 5 divided by 100, so 84% is 5 divided by 100 multiplied by 84. The amount of copper in moles is mass over molar mass. and the number of copper atoms. So the number of particles could be, in this case, atoms, or it could be ions, or electrons, or it could be molecules or something like that. It's just a number of these particles. So that works out as 4.2000 grams. I've retained additional significant figures in process just to avoid any rounding errors. Mass over molar mass for the amount of copper gives me that amount of copper atoms. And then finally, the number of copper atoms is given to us by that calculation. I've mentioned before about the value for Avogadro's number. Also recall the symbol for Avogadro's number is sometimes L, capital L, whereas I've used capital N subscript A. That's the number of atoms, 3 significant figures. Always show you're working out, and that to me includes the equation that you're using with variables, the substance that the equation relates to, so in this case copper, the numbers that you've used, so you can ensure that you can get method marks, in process results to additional significant figures and units. Okay, so the final moles question from this video, we're going to move away from gases and number of particles here, and it looks like we've got a concentration question. So again, they've quite kindly given us a balanced equation. There's also an extra little twist with percentages again. So if this is a little bit unusual, it's essential once again to show you working out fully to ensure you pick up method marks should you make a mistake somewhere along the line. So the first thing we can do is we can work out the amount in moles of lead nitrate. If you look at the question there, we've got a volume of lead nitrate and we've got a concentration of lead nitrate. From that, we can work out the amount of Ki required for the reaction using the balanced equation. And then we can work out the amount of Ki used. And the amount of Ki used, remember from the question, is 10% more than what is needed or what is required. And the concentration of what is used can finally be worked out to get our final mark. So the amount of lead nitrate is equal to concentration times by volume. It's a 1 to 2 reaction, so the amount of potassium iodide that is required is going to be linked to the fact that it's a 1 to 2 reaction. The amount of Ki that is used is 10% plus more than what is required. So work out what 10% is of the required and then add that to the required. And then the concentration is going to be number of moles divided by volume. So 1.50 multiplied by 50 times 10 to the minus 3. So times 10 to the minus 3 is just a conversion because we need to convert centimeters cubed into decimeters cubed. The amount of Ki required is 2 times the amount of lead nitrate. So that gives us those two figures there. The amount of Ki used is going to be an additional 10% on top of that 0.150. So 10% of that is 0.015. So that works out at 0.165 moles. And the amount divided by volume, again, I have used 50 times 10 to the minus 3 there to show the conversion into decimeters cubed. And that works out at 3.30 moles per decimeter cubed.